Hello, Hythloday. Really enjoyed your last video, and I'm really excited to see you making some videos because I just think it's great. I'm studying a lot of this math stuff, and it's not the kind of thing I can talk to my friends about. I talk to matrix multiplication, and they don't know what that is. Um, and there's some really wild stuff going on that I wanted to talk about, and with the math and reality and all this kind of things we've been hinting at. And it's summer now, so I can actually have some time to make some videos. I'll be taking a calculus class, and so it'll be kind of mathy this summer and kind of have some chance to explore. So right on. I really liked what you had to say. I didn't really disagree with any of it, so I'm just gonna get into some things that I've been wondering about, like maybe want to talk to you about, because I'm really kind of confused here on some stuff. So here we have our first math problem. It's pretty simple. 1/2 plus 1/3 equals 5/6. And, that's no big deal, right? Because, one half is the same thing as 3/6, and 1/3 is 2/6, right? So then, boom, 3/6 plus 2/6 is 5/6. Easy, right? But imagine if these were for some sport, like, baseball. Like, the sportsman tries to do it twice, but only gets it one time the first time, right? So this time he gets it, first time he goes 1/2. And then the second time he tries, he tries 3 times and it still only gets it one time, right? We certainly wouldn't say that that's, that he succeeds 5/6 of the time. It's going to be more like 2/5, right? So, basically it's different mathematical rings. In this mathematical ring, 1/3 plus 1/2 equals 5/6. In this mathematical ring, 1/2 plus 1/3 equals 2/5. And it really kind of just comes down to what you're modeling, depending on what kind of ring you use. Whereas a ring's elements and operations on those elements. It creates all the math. So, well, let me talk about some matrices, and then you'll see where I'm getting at. Okay, so I'm going to talk about this non-commutativity thing, where here we've got two matrices. I'll call this one matrix A, and then I'll call this one matrix B, right? A is 1, 2, 3, 4, 5, 6, 7, 8, 9. B is 9, 8, 7, 6, 5, 4, 3, 2, 1. We multiply them together, you get this big nasty thing. Okay, well, if we did B first, right? 9, 8, 7, 6, 5, 4, 3, 2, 1. And then multiplied that by A, right? So the first one was A times B. This one is B times A. And we're going to get this matrix, which is, again, a nasty thing, and it's similar to this matrix. There's 90s, there's numbers, they're the same, but it's a different order. These are, not the same thing. Right, so it's a non-commutative ring in this matrix multiplication, where A times B is not the same thing as B times A. And so I'm going to talk about that with physics. Again, I don't know quantum physics, but what I was discovering when I was looking at the linear algebra, I found this strange thing where this is what Heisenberg did, where he's got rate times distance equals time. That's a pretty straightforward formula, right? But then we do it in the matrix and then have distance times rate equals time. Well, then these two times are not the same time. And that's the Heisenberg uncertainty principle right there. It's why we can't know where something is and how fast it's going simultaneously, because these two times are not the same, is the way I understand it. And so then the difference between them, like rate times distance minus distance times rate, right? Rate times distance minus distance times rate. The difference between these two times, basically, is scalar multiple of I. So some constant number multiplied by I, And this is why all of quantum physics happens in the complex plane. And, we can't throw it out, by any means, because matrix algebra is the best method we have of predicting the motions of tiny little particles. Let me talk about this. This is, where does this I come from? Is this sine wave here, right? Here's sine wave. This is the light wave. Here's our light wave, and it's observing this electron. And because it's sinusoidal, that's where we're going to get our I. When we've got matrices like this one, right? Like when I was talking about, those first matrices, right? Where it was A times B, B times A, and we get these matrices where they're not the same. Well, this is still in the real numbers. We didn't get to I just because we had non-commutative structures. We got to I because of this, and matrices like this. Like this is a rotation matrix. It's got sinusoidal stuff going on in it, and so that's where we're going to get I, and I think it has something to do with Euler's identity. Wait. And because that was derived from some sequence of sines and cosines, trying to find a relationship between them. I don't really quite understand I yet. I'm working on that, but I'm not sure if it's necessary. Here are the matrices from your video, right? So here's that one that does the transformation on this vector, and as we do a series of these, it cycles through the various vectors: 1, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, and 0, 0, 0, 1, and then back to 1, 0, 0, 0, etc. It makes this kind of wavy thing, right, where it's like a discrete wave, as you were talking about. Is reality discrete, right? But it's this spot, this spot, this spot, this spot, right? It's this four-dimensional wave. That is a discrete way to say that, right? I hope that makes sense. So, is the universe discrete? Do we need I? Do we need Heisenberg's uncertainty principle? I'm not sure. If we can, the thing is, like this, your matrix that you're showing that makes this sequence of this periodic sequence is a linear transformation. So it doesn't need sine waves. It doesn't need that kind of stuff. You can do something similar with, foxes eating wolves, and it's a completely linear. Or foxes eating rabbits, where as the foxes eat the rabbits, then the rabbit population dies, so the fox population dies, and then as more rabbits come into the system, then more foxes come into the system, and they eat the rabbits, and the rabbits die, and because they eat too many rabbits, and then the population goes up and down just through linear transformations of the population. I'm not saying that obviously foxes and rabbits don't do math, but and how would they know which ring to look at? All these you can have. There's infinite numbers of different mathematical rings. They're based on elements and then operations on those elements. Except, I was just watching this guy Sergei Siparov, and he was talking to Roger Penrose. Roger Penrose was asking questions after Sergei's presentation, where he has a new ring, I guess we'll call it, and then he doesn't have any elements in the ring. It's just operations, and so therefore he doesn't need a lot of the strange stuff with the eyes in the quantum physics, and he doesn't need the dark matter or the dark energy, which is great, because I think dark matter and dark energy are kind of just our little theoretical patch we stuck up there to try and explain why the universe is accelerating, which still doesn't make any physical sense, because if it was accelerating, well, it is accelerating as far as we know, but if it was dark matter that accelerated the universe, we would need more and more dark matter to constantly come into existence to continue accelerating it. If there was, as far as I know, I mean, on some kind of Newton kind of sense. Anyways, I'm out of time. I hope you can help me straighten some of this out.